Hi everyone, and welcome back. This is Ibrahim Siddiqui, and today video it will be a little bit mathy, so there will be a lot of math, and this is because I'm going to derive the risk response equation for each of these scenario that we talk about it from last video. So I will start with risk response for undamped, which is this one. So I will derive the mathematical formulation of the when zeta or xi equals 0. And then we said that zeta or xi represent the risk damping. So probably now you don't know the meaning of this risk damping, but if you keep following me, then you will realize the benefit of this risk damping in this project control using governing equation. Okay, let's start. Let's delete this first. So we said I will start with this one. Okay, so which means that um, we have zeta equal 0, and it means undamped. So which means risk undamped for risk. Okay. So you know from previous videos we derive the transfer function. So the transfer function, and we said GS, and the transfer function is always defined in the Laplace domain, and we said it's gamma omega n, which is the angular natural risk velocity or risk frequency over over s square plus 2 zeta omega n s plus omega n square. And also based, if you remember, so we said this is the GS. So it has an input, and the input is US, and output will be the distortion S. So which means that W epsilon S, which is the distortion, equal the input time GS, which is the transfer function. So this is input, and this is output. And we want to find the output. We know the input, we want to find the output. Okay, so you may say, oh, this is an open loop. What about closed loop? So we are not there yet, but just we go step by step. Okay, so once we solve this in the Laplace domain, when we solve this in the Laplace domain, then we will use Laplace transform inverse. So Laplace transform inverse means if you transform from S domain, Laplace domain, and you do the inverse, and then you get the epsilon t in the time domain. So from Laplace domain, which is a complex domain, And when we say complex domain, means S has sigma plus minus imaginary um, axis here time omega d. Okay, but this is in the Laplace domain. Then we do the transformation to go and find the epsilon t. This is what we are looking for. Well, we want the mathematical expression in a time domain. Okay. Why we are using the this technique? Because it's very easy to solve differential equation in the Laplace domain than in the time domain. In the Laplace domain, as you are going to see, is quite easy and algebraic. And but if you go to time domain, it's too cumbersome, too complicated. You will be dealing with integration, and we don't want that. Also, not that for some people, probably they will say, "Oh, this is mathematically, it's not has nothing to do with the practice." Etc. I'm not listening to this negative comment. Here is the in the practice you are not going to use this, but if you are really a good project control, um, you have to understand the foundation. The foundation for the methodology that I am proposing, which is totally different than the traditional approach. If you agree on that, you are the most welcome. Follow me, and you will learn very interesting stuff. If not, it's up to you. Okay, so all right. So we said that we are looking for this expression. Okay, but before that, let's do some simplification. And we said last time that US, um, so let's say UT equal 1. And we said that UT is epsilon D, is a desired distortion. So, and then we said we can model this desired distortion. It can be constant, polynomial, trigonometry, etc. But to make things simple for our mathematics here, so keep it simple, we will say it's 1. And also we will assume that um, gamma equal 1, so which suggests that the risk appetite sensitivity factor for historical equal risk appetite sensitivity factor for the budget system. Okay, so, and we know that gamma equal CH over C of the system. So, and this equal to 1. So these are the assumptions that we make, and the reason because we want to make things easy. Okay, so in this case, so we say that omega epsilon, the distortion defined in the Laplace domain, equal u in the Laplace domain time g in the Laplace domain. So which means that what is the Laplace domain for a constant? I mean, what's the US? Because here I said UT. So you can see here is I'm talking about t equal 1. It's not the time equal 1, but the epsilon d equal 1. It's a constant. If you do the Laplace transform, what you will get? You will get 1 over s time what's GS? Also by making gamma equal 1 equal omega n square over s square plus 2 omega n s plus omega n square. Okay, so this is the distortion in the Laplace domain. Okay, now because we said that we are going to solve for risk and damp, means zeta equals 0, then we just make zeta equals 0. Okay, so when we make eta equals 0, then what we'll have, epsilon s 1 over s omega n square s square plus omega n square, right? So this is what we okay, so this is the expression that we get when we assume that the risk damping zeta equal 0. Okay, here then, so in the control theory, they are very, okay, let's draw this. So if you remember last time, we said that S is a sigma plus minus I omega d. So minus sigma plus minus I omega d, where sigma equal zeta time omega n, and omega d is omega n square root of 1 minus square. And if you plot this in the C plan, on the C plan, complex plan, so this is the real of the S, and this is the imaginary of the S. So basically what you get if you put this equal to 0, so what you get omega n, omega d, it's imaginary because of this, so it will be here. So we get omega, this will be omega n, and then minus here, minus c omega n. So basically you get this. You get 1 here and 1 here. Why? Because it's a plus minus. So this is in the C plan. Okay, this is the expectation. Okay. And so when you solve this, what you get, so when you solve this, just a second here, I think I made a mistake here, because when you solve s square plus omega n square equals 0, then s equal plus minus I omega n, right? So I'm sorry, so I made a mistake here. This is not in this case. Okay, so this is not this case. So here we have S, which is here. So we have 1 here, and then we have 1 here. So which is, so let's, this is I omega n and I omega n. Okay, so which means it's purely oscillatory here. So maybe we'll not see the outcome of this because you didn't do the control system, but this is an indication of this. So we can expect that the curve will be oscillatory with fixed amplitude, with fixed amplitude here. Okay, but anyway, so this is how it, and we call this as zeros and poles. So I don't want to use this terminology right now until we derive all the expression of the distortion. Okay, so let's continue. And what we will have, okay, so in order to do the the inverse of the Laplace transform, so we have, this is what our plan is, to get the inverse of the Laplace transform of epsilon in the S, which means the Laplace transform of 1 over S time the Laplace transform inverse of omega n square over S square plus omega n square. And this will equal epsilon t. And this is what we are looking for. But now, what is the inverse of the Laplace transform? So before we cannot do directly. If you did Laplace transform back in your mathematical course at university, you remember that there is a table. There is a table, and there are typical function in the time domain, and then here in the Laplace domain. So let's say, for example, 1. So is 1 over S. And then if you have exponential, you have something, and so on. So, but we don't have this one. So we have to do something called partial fraction. So we have to do partial fraction. So I'm not going to teach you what is partial fraction. You have to do it by yourself. The reason it's quite cumbersome here, but you can do it by yourself. I will just give you the result here. So we can say that epsilon s equal a over s plus b s plus c over s square plus omega n square. And when you do the partial fraction, you get a equal 1, b equal -1, and c equal 0. So, and then when we substitute, the reason we do partial fraction because we cannot do the we decompose the this expression to make it easy because we have a systematic table, standard table, and then we just replace the value, the expression from Laplace domain to time domain. So here equal 1 over s and then we have minus s over s square plus omega n square. And then if we do the inverse of epsilon s, so which means we do the inverse Laplace transform inverse 1 over s minus transform of s over s square plus omega n square. And we know that this is 1, okay? And well, minus, and we know this is, sorry, we know this is cos omega n t. And everything is timed by ut. And then we said ut is 1. Okay, so so which means that epsilon in the time domain equal ut. We always put this ut even though it is 1. Ut is the input. 1 minus cos omega n t. So this is the mathematical expression of the distortion when zeta equal 0. And you can see it is purely oscillatory here. There is no damping or so we have this first expression when zeta equal 0. Okay, so now when we do the same thing, okay, now we go for this one, and which is underdamped, which means zeta is between 0 and 1. So which suggests that epsilon s equal 1 over s, the whole expression, omega n square, s square plus 2 omega n times s plus omega n square. Here also we have to do partial fraction, and also I'm not going in a detail here. You do it by yourself, but we have to do some modification. So we will say we'll add some component. We add and we subtract. So we have 1 over s. I will just do some modification, but we keep the same result. So we have s square plus 2 omega n we add omega ns plus omega n square, and then I will add plus 2 omega n, sorry, I will add this. I will add plus omega square gamma square minus same quantity. Okay, and then we collect term and we factorize 1 over s. So when you do the factorization, So you get something like this, S plus um, omega n square plus omega n square 1 minus square. And these can also be written as omega n square s plus omega n square plus omega n 1 minus everything square. So it's just plus minus of this term that we can rewrite epsilon s to this expression. Why we do this, you will see next. Okay, you remember that we said omega d is what? Is omega n square root of 1 minus square, right? And then also we said sigma is zeta time omega n. So let's substitute these two into this distortion, define the Laplace domain. So 1 over s. So we have omega n square. So, and then we have s plus sigma plus omega d square, right? So we didn't do really fancy things here. We just playing with algebra. All right. So so now when we plot this in the Laplace. So here, then I see something like this. And we said that you will have, so here, then you will have another one here. And this, we said it's I omega d. And this is sigma. And then we have an angle here. Say, let's say this is alpha. And if you remember, we found that this radius, so if I take the norm, which is the square root of sigma square plus omega d square, this is just Pythagore. And we found that, keep in mind that this is imaginary for S and real for S. And if you substitute, so this will be like this, omega n square plus omega n square times 1 minus zeta square. And if you do the result, you get omega n. Okay. Okay. So, but we can now we can say that if I want to express this sigma is what is it's an adjacent to so which means we can say cos alpha is what is the sigma over omega n. So which means sigma equal omega n cos alpha. Same thing, sinus alpha. Sinus alpha, it means omega d opposite omega d over omega n. So what means? It means that omega n equal omega d equal omega n sine alpha. Now if I do tangent alpha is what? Tangent alpha is opposite, which means omega d over sigma, right? Over sigma. So which means that alpha is tangent, the arc tangent of omega d over sigma. This is just basic trigonometry, okay? No fancy here, all right? And then we will use the partial fraction, so which will give us the same thing as before. So we have epsilon s equal a over s plus bs plus c, and then we have s plus sigma square plus omega d square. And if you do the partial fraction, you will find a equal 1, b equal -1, and c equal -2 sigma. So you substitute epsilon s, so 1 over s plus minus s minus 2 sigma, basically plus, and then this will become, so this will become minus s plus sigma square plus omega d square. Okay, so then we can decompose further, say 1 over s minus what you can do here. So I can say, okay, so so I can say s plus sigma over s plus sigma square plus omega d square, and which can be written 1 over s minus, and I have s plus sigma over s plus sigma square plus omega d square minus, I have sigma, and I have s plus sigma square plus omega d square, and then I will add omega d, and then I divide by omega d. Then I can final decomposition, s plus sigma over s plus sigma square plus omega d square minus, then I will have sigma over omega d, and then time omega d over s plus sigma square plus omega d square. The reason I'm using this because there is easy, as I told you in the table, we do have an expression looks like this, and an expression look like this, and an expression look like this. So that's why we write it in a way that fit the purpose, basically. Okay, so now if we do the inverse, so we know that the inverse for 1 over s is say ut. The inverse, the Laplace transform inverse of s plus sigma over s plus sigma square plus omega d equal, let me check my table here. It will be exponential minus sigma t cos omega d t time ut, and the Laplace transform of sigma over omega d is omega d s plus sigma square plus omega d square, and this will be, let me check, it's the same thing, so it will be sigma over omega d exponential minus sigma t, but this time sinus omega d t ut. So I guess, I hope that I did not make any mistake. Let me double check. Okay, so I think I'm correct here. So if I sum, so epsilon in the Laplace in the time domain now, okay, because this is time domain, time domain, time domain. So equal ut time, we have 1. Keep in mind that we have a minus here and a minus here. So minus, the first one, exponential minus sigma t cos omega dt. And then we have a minus, but this time sigma over omega d, exponential minus sigma t sinus omega d t. And we can make the exponential in common. So ut 1 minus exponential minus sigma t. To keep things simple, so we multiply and divide by omega d, and this will give us omega d cos omega d t plus sigma sinus omega d dt. Okay, so yeah, now so we have an expression based on the omega d and sigma. But let's do further simplification. Okay, so keep it like this, and then we will bring back the things that we have done here. So we have an expression of the sigma in term of omega n and cos alpha, omega d, omega n, and sinus alpha, and we know the alpha based on omega d and t. So if we substitute this into the this expression. So let's change the color or keep it the same. So equal ut. So we have 1 minus, we keep this same, minus sigma t over omega d. So we said omega d is what? Omega d is omega n sinus alpha. So it is omega n sinus alpha time cos omega d t plus what's sigma? Omega n cos alpha omega n cos alpha, and we have sinus omega d t, right? Okay, so what can we do also? What can we do to keep it more simple? All right, so we can see that there is a omega n here and another omega here. So we can bring this in the front. So it become t equal u t 1 minus omega n over omega d exponential minus sigma t. And we have cos, so we have a sinus alpha, and then we have cos omega d dt plus cos alpha, and we have sinus omega d et. And we know this expression. This expression is very famous, and this is just sinus omega d t plus alpha. All right, so now it become more clear. Epsilon t equal u t 1 minus omega n over omega d exponential minus sigma t time sinus omega dt plus alpha. Now what is alpha? So if we substitute everything now based on omega n and risk damping zeta, only with these two parameters. Okay, so the last simplification will be ut 1 minus what is omega d? Omega d is, so I will write it here, omega d is omega n square root 1 minus this. So if I substitute this here, so I will get only 1 minus square. And then here I will get epsilon exponential minus omega t. So we know that sigma is omega n. Okay, and then time sinus, what is omega? It's omega n 1 minus the psi time t plus alpha. What is alpha? Alpha is arctangent of omega d over omega d is what? Omega d over sigma. So what is omega d? Is omega n 1 minus. What is sigma? Is xc omega n. So alpha is arctangent of depend only of the system, the risk damping, and which is arctangent of square root of 1 minus square over c. Okay, so it's quite long, but it's worth it. So we have this expression and we have this expression here. What they mean. If you have sinus or cosine, this is oscillatory, right? This is purely oscillatory. So which means that this is if you have, let's say you forget about this. So assume that your epsilon t is only this. So which become like the one that we derive previously here, because cos or sinus is almost the same. So we become purely oscillatory. Okay. However, this expression has two components. So it has this component, oscillatory, and it has this component, which is the envelope. Which is the envelope. And then we have this, which is the steady state. Steady state. This is so, which means when epsilon t, so which means that when t goes to the infinity, the expression will go to the steady state. To the steady state, and the steady state here is ut. So which means your desired distortion. However, but and all of this is also called the transition. Okay, so all of this is the transition. This is what is hidden from the project control. But now it's no more hidden. Now things are clear. At any given time, you know what's going on based on your based on omega n, your risk frequency, because remember this is 2 pi f, and f is what? 2 pi x0 over f0. So it means that if you know the budget, you know your indirect cost times by 2 pi, you get your omega n, and then you know which is v0 to x0 f0. So if you know this components of your cost, you know how much risk damping that you have in your system. You plug only these two parameters. Here you go. You know how the evolution of your distortion. So which means that you can simulate and you get this type of curve. It all depends how your the cost, your budget, the ingredient that you get. But what you will get, you will know the maximum amplitude, you know the time when it will settle based on your epsilon d here, or your desired distortion. And you have the envelope. And we know the expression of the envelope now, which is this one. We know, we just define it, which is this. This is the envelope. So which is minus, so which is, yeah. So here is exponential minus c omega and t over 1 minus. It's only with two parameters that you know the evolution of your distortion over time until the finish date of your activity. So this was hidden. Now it's not hidden. Now you can see at any given time what could happen to your cost, because this is your distortion, is epsilon t. And in many occasions, if you were following me, we said that delta x, the cost variation, is your x0 time epsilon t. So we do have the risk premium as a function of time, because this is risk premium as a function of time, because the distortion, we know now the distortion as a function of time, and we know how it behaves. Okay, so we also know the actual cost or forecasted cost, and we said it's x0, 1 plus minus epsilon t. So we know the evolution of your the cost, how it's gonna vary. It's very amazing. I mean, so even though the mathematical here, maybe you see it as a cumbersome, but it's not important. So the most important, because you are not going to do this by hand. You are not going to see this in your daily practice, because everything here will be done through program and computer. So it's just you plug your omega n, plug your psi, or just plug your ingredient. And probably sometimes you don't have this. You need to evaluate this. So this is how much risk damping I am willing to put. Okay, so you get this. And how much fixed cost that I have to pay regardless of the productivity. And you know your budget, what is my total budget, and then you plug everything here, you get your distortion. So you get the risk response through this curve, and then you look at your response, and then you say, oh, I see a big jump here. It's an overshoot. Now you say, how much overshoot you have? Oh, if it is high, it means that your project is not, I mean, your budget system needs some revision. And then you look at the time, might surprise you, because there is a relationship between, already there is a relationship between your cost, between your schedule, and between your risk. It's a full integration, cost, schedule, risk. And the type of, this is in case your zeta, your risk appetite, your risk, your risk dumping is between 0 and 1. Now, what if my risk dumping is 0? So you have something there like this. And what if the risk damping is 1? You will have something like this. What's the expression of this? So we can do the same thing, and we can come up with this. So let's do it now. So this is the last one, and I will let you go. So now let's zeta, the risk damping equal 1. So which means GS equal omega n square, S square plus 2 omega n S plus omega n square. And then we said this equal to 1. This is 1. So it's going to change. So this become omega n square, S square plus 2 omega n S plus omega n square. So, but epsilon S, based on the assumption that we made previously, so 1 over S times omega n square, S square plus 2 omega n S plus omega n square. So you can see that zeta here equal 1. And then we do the partial fraction over S plus B over S plus omega n plus C S plus omega n, because this can be factorized. You know, S plus omega n square equal S square plus 2 omega n S plus omega n square. See this? And look at this. Same. So we can write epsilon S, we can write this as 1 over S omega n over S plus omega n square. So we can write this. And then we do a partial fraction. We get this expression. But when A equal, we found equal 1, B equal minus 1, and C equal minus omega n. You substitute and you get A over S and minus 1 over S plus omega n and minus omega n over S plus omega n. You do the transform. So the transform of S equal T, which equal the transform inverse of A over S minus the transform inverse of 1 over S plus omega n minus transform of omega n S plus omega n. And of course, everything is multiplied by ut, and this is what we will get. So epsilon t will equal to ut 1 minus 1 plus omega n t exponential minus omega n t. And if you draw this, you will get, if this is your omega d, and you get this. Okay, and you can see there is no cos or sinus here. It's only exponential and factored by omega n t. And what is omega n? We said omega n is 1 over x0 over f0 square root. Very easy, simple. So you get the distortion, you get the expression of the distortion, you get a response here. So all of what we get here is the response. And then we can analyze. This is a time, and you do some other calculation that we will do it next time. Hope that everything is clear. I know that this video it's more mathematics, but this is just for your information. You don't have to worry. You are not going to use this in practice, but it is good to know what you are doing when you start analyzing the cost and also building your estimates when you bring everything together. Next time we will do how the design specification. So basically, we will find what is the overshoot, what is the time, the mobilization time, what is the settling time. Settling time is basically the duration. Uh, what is the overshoot? What's the maximum of your distortion? Um, I mean, and other things. It will be also mathematically driven, and we derive from it very interesting formulation that we can use later on to design our budget, estimate, quantify a risk, design the schedule. And on top of that, if you put all of these together within a project that has, I don't know, thousands of activities and using computer application, it will be very quick to get an estimate based on certain assumption. We always have to do assumption. We always have, it's like you are designing a bridge or you design a building or a engine, is the same thing here. So what you want to control the risk premium. You want to control the delta X. So if you have certain risk tolerance, so what is your risk tolerance? It has to be quantified, not based on your gut feeling or what you can rely on your historical data. And I mean, there is a billion opportunities here that we can do by using this control system theory because we do have the governing equation. We are able to do that because we have the governing equation. All right, so talk to you soon. And if you like this video, please, um, I don't have to tell you, I'm very shy on that. Please subscribe and hit the button like. Thank you.